Did you send you emails probably?
Many thanks for the detailed answer. I will meditate on the road back to Fargo and develop an answer.
What was your question?
I asked him if he had any books on junction potentials.
Oh, I think I saw you emailing about that in analytical.
Yes. Because I had to learn about junction potentials, or I have to learn. No.
9? Yeah.
Aren't you just on top of your shit?
9. I think he said 9 as in no.
Okay.
I'm doing that today. Because our lab got canceled, I'm just going back. Be responsible.
Started it last night, but then I had a breakdown about hating my roommates.
You really hate your
Because they're gross.
They do.
They're so gross. They're so gross, and I've had enough.
And how
Yeah.
they grow.
Screw them.
Guys, David's gonna walk
Is
out
it
in 2
recording on?
minutes. At
Yeah, recording's on. I'll
11:03,
tell you later, friend.
at 11:03, he's gonna walk out and not come.
Okay, we're ready now, David. Sorry.
Don't worry about it.
Apparently the mic is still not working,
Okay.
Oh,
and I don't know why.
Yeah, Yang threatened us a couple weeks ago that says if we're not quiet by 11:03, he's gonna leave, and then we're gonna have to make up the lecture on our own.
We'll just have someone go up front and just start lecturing.
Go grab Zoe.
Hey, get Zoe from the lab.
That is way higher than I can reach with my hands.
There's a laser
The
pointer.
laser pointer works.
Yeah.
So what we're looking at today, so you have your methods that you've been using, so the Schrodinger time dependent, Heisenberg equation of motion, and then the systems you're working on. So today we're going to look at the time dependent particle in a box and introduce the density matrix that we will use for it. So if we look down here at the bottom, we have our solution for the energy and wave function for the time independent solution for the particle in the box, which you hopefully solved in a previous class.
probably, yeah.
Probably.
But what you have here, so you have your initial state, so here we have our box with a potential of 0 inside the box and infinity outside the box. And you also have your kinetic energy, which is shown there. And then you would solve this equation using our boundary condition. And that's how you would get these in the end. And you do that by using this general solution here based on Euler's method, where the C plus and the C minus are the expansion coefficients. And if you go through and solve it, we see that C plus and C minus are opposite of each other, so they're same but opposite sign. And so when we go through and see here, we see that this term goes to 0 and this term goes to 2, which is where we get this. And then when you solve for the expansion coefficient, which is right there and very not easy to read writing, you see that the expansion coefficient is imaginary, and then you can get this out of it. And so we have our final equation where we have the normalization factor and then a sine curve dependent on n, where n is excitation level, or an integer, a positive integer, or non-negative integer technically. 0 is a possibility. So then, if we go David, could you please describe the wave function step by step?
Is that from Dimitri?
No, that's Yulin.
Oh.
I definitely could. I'm not gonna have enough time to finish the rest of the lecture if I do.
Right. Yeah, we kind of don't.
Yeah.
He'll
save like 3 minutes to go through the slides.
he'll normally derive everything like on the whiteboard. And then the last 2 minutes, he's like, all right, that's enough time to go through the slides, and then he'll just fly through the slides in the last like 2 minutes. Yeah.
Yeah.
These are.
So if we wanted to derive the wave function, so first you take these values, which are a guess solution or a general solution. We use Euler's method to convert the exponential to cosine sine. And then we just separate it out into the cosine and the sine terms. Then you would need to solve for C, which is done in this line here, although it's a bit shortened. And then when you would plug that back into this, because if we look here, because these are opposite sign, this term cancels, which is, I don't think that's actually shown anywhere. But the C plus and C minus are the same except opposite sign. So the cosine term cancels and we're left with 2i C plus sine term, which is what we get here. So if we plug the C that we solve back into this, we get this equation here. And this is just writing it again. So the bulk of today's lecture is going to be on looking at a superposition of two states of the energy of the particle in a box. We're looking at what we can actually get. So we start with our wave function, which is nice, useful, but it's very hard to conceptualize. So if we want to conceptualize something, we need to move into something else. In this case, we're going to use distribution in space. So the wave function squared. And we're going to see that we get two different factors. You get the time-dependent factors and then the spatial factors. And that's going to be the introduction to the density matrix. So here is what you are, I don't know if I can say it with just letting you know I can't.
The video, are we gonna get rickrolled again? No, we're not.
So here is the expected result for what we're doing, and I believe you are going to be making this in lab today. I'm not positive about that. So with our initial conditions, which we'll get to in a couple slides, you see that we have a system that's oscillating between these two modes in a alternating fashion. So if you were to look at the expectation value for the position, you'll see that it's oscillating between about 0.3 and about 0.7.
I know.
So if we look here, yeah, it is rotated weirdly. If you look here, this is about 0.3, this is about 0.7. This axis is the expectation value and this axis is time. So as you start at our initial condition, it goes here, and then it just oscillates between the two. So it's basically looking at where the peak of this is through time. So it's going from here to here to here. So if you look at this, you'll note that the area under the curve is staying the same because, and assuming it's normalized correctly, it's just 1.
Right.
So here we're looking at, again, we have our time independent solutions to the Schrodinger equation for the particle, 1D particle in box. We have our energy, we have our wave function, and graphically, the way these are usually done in literature and teaching science in general is that you'll have a combination of the y-axis where you get the energy plus the wave function or plus the probability. It depends on who's drawing it, which one you get. So if we,
Whoa.
Oh, yes.
you end up with a graph that looks like this.
Wait, what? Oh, were you gone?
There a
He
question?
was gone on Friday.
He plugs all these like equations and graphs into this like AI art.
And it like makes
Generator or
this,
something,
he
and
had
it
like
changes
20 on
it.
the last.
Yeah,
So you have this. So if we look at our equation here, we see that this first term is effectively a constant. And the only thing that changes is this n squared. So when n equals 1, it's here, n equals 2, the next one would be at 9. And then what we see is that they have this probability or distribution at the peak for that energy level. So each of these lines is an energy level, and then what's drawn on it is either the wave function or the probability. So if you don't draw it, I make this disappear.
There you go. I think if you open and close the chat, it'll go away.
Oh, facts.
Cause like with the notification on there.
So if we look at this one, you see that we have the same thing. So we have the n equals 2, n equals 1, and the n equals 0. So the blue is the n equals 0, this orange color is the n equals 1. So we're seeing the same thing, except we're not seeing it offset by energy level. Where here they are offset by energy level, and in most textbooks and like general online websites will show this form.
But the areas are the same
Yeah.
under the curves.
Yeah.
I don't have that equation in here.
So if we switch here, so here, the one that we've been seeing.
Will you go back one slide?
Yep.
Oh.
So we see that this, what I have highlighted in green here is effectively a constant. I mean, L and M will vary, but they're constant for the same system. And everything else is a straight constant.
Okay. That equation didn't show up on the slides, so,
Did it not? That's weird.
no, at least not when I like.
Sometimes they kinda-
input it.
It's the same as this equation, it's just I rewrote it.
Yeah, oh,
Yulin is wondering about N. I did misspeak. Yes, you're right, Yulin. It can't be 0. So it has to be 1. So here's 1, here's 2. So if we look at this graph, you can see the other major one that you occasionally have, which is the probability. So previously we were showing wave function. Now over here is probability. So what that's doing is it's keeping everything positive because it's the wave function squared. So you're expecting at n equals 1, the main thing, it'll primarily be located in the middle. At n equals 2, there'll be 2 peaks off to the side. If you go up to n equals 3, there'll be 3 peaks with 1 right in the middle. So this is describing spatial distribution of the wave function. It's not working for some reason. So then for the main portion of what we're working on, if we look at our particle in box well with our 2 wave functions, we see that we have the ability to create a superposition because a general solution or a particular solution is just the sum of any general solution. So we can create a wave function that's a superposition of state 1 and state 2. So this this equation makes sense to everyone sitting here? Any idea where we get the 1 over square root of 2?
It's pi over 4. Sine of cosine. pi over 4.
No.
The only thing I could think of.
Any idea where the 1 over square root of 2 comes in? Do you understand what the one ket and the 2 ket are indicating here? So the first state and the second state. So that is what the kets are indicating. So do we have an idea why we have this 1 over square root of 2? Any idea? So what that is, that's normalization factor.
Oh,
So
Oh, is that why okay, C1 equals C2 equals 2 to the negative 1 over 2.
yeah, so in this case, yes. So what we're doing is we are creating a system. Our initial state is going to be 50% in state 1, 50% in state 2. So then if we go here,
I have a question. Why is it 50% in stage 1?
what was that?
Why is it 50% in stage 1 and 50% in stage 2?
We are choosing that. So the idea is if we take, say, a laser and excite our system. So if we shine a laser at our system, what's it going to do to the electron or the energy in general? It's going to excite it. So if we shine a laser at it a long time or a lot of laser at it, it will approach complete excitation. But if you do it in a short period, or there's a lot of something that would cause it to only partially excite, we're simulating that state where it's only partially excited. And we're choosing, partially for simplicity, 50-50. And so because these are both equal, we can see that they're the same amount in each one. And if we go on to this slide, which I haven't covered up.
What do you mean you can't?
Those equations should be on the slide. I don't know why they wouldn't be.
Mine is even worse than yours.
Oh, sometimes when you upload them like into Notability, it just messes it up for
Yeah.
some reason. So
So
it's not Dimitri's fault, it's fine.
in the slides I was sent, these were handwritten. I did retype them so you could actually read them.
Yeah.
So in some textbooks, this is how they would explain to do normalization in this, where you're doing the sum of all the expansion coefficients squared. So if we were to calculate that out, we get 1 over square root of 2 squared plus 1 over square root of 2 squared, which equals 1. That's why it's 1 over square root of 2 instead of just straight 1/2. Something wrong?
no, we're okay.
So then these are the equations for the states. So you notice if we go here, you see that it's the same equation here, although we replaced x for z. And we've also factored in the n. So here n equals 1, here it equals 2. But you notice otherwise it's the same equation as we were showing previously. So the question then becomes, how do we see what happens as time goes along? You have a method to do that? Predicting what? I mean, that I suppose is technically a way, it's not a very useful way.
Oh.
Or it's probably going to be inaccurate a lot of the time based on most people that predict the future. Otherwise the world would have ended like 10 years ago.
That is facts.
So we need to use the evolution operator, time evolution operator. So here we have the time evolution operator laid out. So you notice it's e to the minus I, and you notice it's factoring in the energy, so they are different. So here it's E1, here it's E2. And as a whole, we can call this portion right here the time-dependent evolution operator. Time-dependent expansion coefficient. So with that, we are looking for this. We have our equation that we're trying to solve to determine any relevant observable that we're interested in. For instance, density or expectation value of position are two of the most common ones you'd be interested in. So, does that make sense? So, as an experiment on how to do this, we are going to determine the dyadic solution to, or form a dyadic calculation instead of a scalar, which means we're going to take the ket times the bra. And you have had an introduction to Dirac notation, correct?
Yeah.
So here we're taking the ket times the bra, which is going to give us a matrix. Unlike the bra times ket, which gives a scalar. So. So here we're taking this, the bra times the ket aside. So we're ending up with a ket term, or a ket term here and a bra term here. And then what all this is we're just opening these brackets. So we have the first times the first, first second, second first, second second. So just basic algebra there. And you'll notice that for these bras, we're taking the complex conjugate. So what is this star is indicating?
Complex conjugate.
Wonderful. And the bra is also indicating the complex of the ket. So we see that we are taking the laser pointer. We see that we're taking the complex. We're taking C1 times its complex conjugate. And if we remember earlier, that's there's also a square root of 2 factor here that I'm not writing. What we end up basically with this is our C. So if we were to take the complex conjugate of this, what is the complex conjugate? What would we need to do to take the complex conjugate of this?
You just changed the sign, don't you?
Change the sign of what?
I know.
Change the sign of I.
Yeah.
Good job.
So what happens when we multiply these two together? So
Wouldn't you just get one in the eye and then everything else?
so what happens here?
It would just become En. When the En T over H bar just becomes squared and then the I just becomes something. Because it becomes I squared, but it becomes negative.
Well, how do you do multiplication or exponents? Oh my God, you add them together, so it's zero.
That's what I was going
Right.
with. 0
Right.
and 1. Thank you very much.
So you end up with e to the 0 to the 1, which I don't know what you said, but one of you said.
I did not, it was wrong. I don't know what the hell I was thinking.
So we see that when
It's a Wednesday.
they have the same n value, we get 1 for this portion of the term. And do remember that this is only a portion of the the expansion coefficient, there is also the normalization factor, which I've taken out of this discussion. But this, the time evolution portion goes to 1.
It broke again.
All of our tools.
Oh, gosh. Oh, Grace. Oh, Grace.
Why are you saying base?
Don't worry. That's my sister's making.
I did not ask.
Sam?
So what we're going to do
I answered.
is. So another one of
I
these
love
wacky
that.
graphs.
It's
That
like,
could be like
it's
a
like,
wallpaper.
yeah, it's like the.
So if you look, this equation is just being copied right here. And we're going to split, what we're going to do is we're going to convert these terms into what we call the time and the spatial factor. So what we're doing, if you look at this right here, this portion, you see that it's the same. We're converting from Dirac notation back into your more normal notation that you'll see. So this would be the equivalent of the bra. This would be the equivalent of the cat. Or other way around, really. But so what we're doing is we're trying to solve probability. So if we go through, and this is probably, if you look in most standard undergrad P-Chem textbooks, you're going to see this form for solving that. But what we're interested in here is this portion right here. And that's what we call the density matrix. So if we do the trace of that, we end up with our probability. And it's called the density matrix because another way it can be thought of is as the density of the electron in that space. So then what we're doing is we're just using this and the values we previously determined to write down this equation. So then what you get is you get two different sets. You get this, all these expansion coefficients, which are time dependent. And then you get these phi's that are space dependent. So they're called the time factor and the space factor. So what you end up with is in this one, you end up with a term that's generating phase. All these E to the I, ENT terms are generating phase through the model. Where in all these phi terms, if you remember back to earlier, the phi is just the square root of 2 over L sine pi n L. So you end up with a bunch of sine squared terms. And it varies slightly depending on whether they're the same or not on what, if there's a 2 involved. So here would be phi 1, phi 2. So some of them are, so it's not necessarily sine squared, it's 2 sines, but you can, so this is sine squared, this would be sine squared, and this would be 2 different sine curves. So what we need to do is bring all of these out, which it actually shows right here, I guess. And you can see we have this set up. And over here, we have the rows, which if you are doing this type of work, you should know that rho is density. So these are dense, time-dependent densities. And here we have our spatial positions. And down here, we have basically what we did over here. So we're solving for these blue boxes. And you notice in this one, we do have this normalization factor included. So we see that this portion goes to 1 times 1/2 is 1/2. Same thing with this bottom one. And these ones, you get a bit more complicated term because the exponential doesn't vanish. So what we see if we take our initial state, which was 1/2 in state 1, 1/2 in state 2, we see that if they were all in one state, it wouldn't change because the time evolution goes to 0 or it goes to 1. So that's why we needed it in 2 states, so we could get a change throughout a change in distribution based on time. And we see that there's both of these have that distribution. The difference is the energy factors. Here it's E1 minus E2, here it's E2 minus E1.
Why is the first one E1 minus E2?
It's based on pulling out the negative.
Not like, sorry, not the very first one, the row 12. In the bottom right.
Cause you have IE2T.
Yeah, I'm looking at that. That looks like a mistake and that I didn't catch.
It's e to the I E2T over H hat minus or times e to the negative I E1T over H hat. And so it should be
So you-
E2 minus E1.
Yeah, as I'm looking at, that's a mistake. I didn't catch when I was looking at the
Okay.
slides.
But you pull out a negative I, so
Yeah,
it should switch the sign.
Yeah, exactly. It should switch the sign when you know the negative I. It's correct.
No, yeah, you're right. So,
Minus 1 also.
Plus 1 Patricia and plus 1 Melody.
so what you have is that from the first one. So what we're doing is we're pulling this negative out. So this one would become positive, this one would become negative, and we're multiplying by a -1.
Oh, okay, that makes sense.
And it's just rewritten so the negative term is second.
Yeah. Understood. Good job. They're echoing.
So then what you end up with is this is same thing, more the same, but you end up with 2 terms that are time dependent. And generate phase. And then you end up with these 2 terms that don't,
I have a question.
yep,
I don't know, doesn't it seems like the value for row 1, 2, and row 2 were similar? Like, why does it have to be different?
row 1, 2, and 2, 1.
Yes.
Why does it have to be different? Because this.
I mean, the energy state, like, it's as if it's exciting and relaxing.
Yes, so the time evolution operator is dependent on which energy state it's in. And I do not see the equation I'm trying to find. There it is. And we see that energy is dependent on which state it's in as well. So the energy of the different states is different. And the time evolution operator is dependent on the energy in addition to the other factors. So I mean, you can actually, right here, we have the equations for E1 and E2.
Yeah, I understand. But I mean, is it not the same energy when you're moving from E1 to E2, the same energy as E2 to E1, like the excitation is the same energy.
The energy amount is the same, the signs are different. What's that before? that's about where we were. So yeah, so yes, so if you were to think of this as a delta E instead,
Yeah.
you would see that this one would be delta E. Actually, this one would be delta E based on how we normal convention, this one would be minus delta E. Are there any other questions?
No. Roger, you have a question?
So now we're focusing just on the spatial terms. So if you remember before, we had this 1, 1, 1, 2, 2, 1, 2, 2 with the conjugate, with the first term being the complex conjugate. So if we were to graph these, you see that the first one and the second one are just straight sine squared terms. You end up with this positive sine curve or sine squared curve, I suppose, technically, for those two. So these colors are matched with the outlines. So this blue curve would be the spatial position for this one. This curve would be the spatial position for this one. And then this curve is pretty hard to see, but that's also got the yellow curve in it. Would be these two. So what you see is that there is, due to the time dependence and accumulation of phase from the C terms, the expansion coefficient terms, we get a constructive or destructive interference of these terms, specifically from this, especially from this one, this purple and the yellow one. So as you add up, these terms change as a total, because we're adding all these terms to get the total. So as we were to add these, we'll get constructive and deconstructive interference, and because these two accumulate phase, how much they're constructing and deconstructing interference varies with time. So this is saying basically the same thing, except in words. You're getting these deconstruction and construction. So you have these spatial factors, which we showed are fairly static. And then the time dependent factors, which were the expansion coefficients. They vary. So the reason you're interested in doing this for this system, it's not super useful, but if you go into something more complex, this is very useful. So what I have no idea what this slide is about. I don't remember this slide.
It says Euler. Sort of.
How can you read that? That's like my grade on standard.
Yeah, I know. Practice reading this. Scribbles like my.
Oh, this is.
Yeah.
So anyway, what you end up with once you factor in the change, so we have those 4 graphs that we showed before. But that one graph that had the positive and the negative peak is now varying with time. So we see at the initial time, it's there before going to there, and then going back and forth. So we see as it's getting close to our barrier, it's repelling it, or you can think of it as repelling it. So when it gets over here, it's getting close to here and it starts moving the other way. And when it gets over here, getting close to over here and starts moving back toward the initial position. And we see that you don't really have anything bumping up against the walls Which if you were just expecting a standard sine curve where moving and reflecting off a wall, you would expect it to reach all the way to the wall before coming back. Where we don't see that in this situation. And that is
Meeting.
the end of the lecture. There were a couple questions from Yulin. Are there any questions from you before I address Yulin's question?
Negatory Ghost Rider.
I don't know what that was, but I hated it.
Fred, any questions?
Why are we here?
Any questions, anyone else in all of these?
You're not, no,
I assume this is a required class.
unfortunately,
What's our purpose? It wasn't.
not unfortunately, we get to hang out with Dimitri.
So
thanks.
PChem,
That makes it worth it.
and I assume this is the quantum side of PChem based on the fact that Dimitri is the teacher,
Correct.
is very is what determines how basically all of your machines work, like IR is a PChem technique that's been expanded to be used in OChem. Same thing can be said for UV-Vis and all the others. They're PChem techniques that have been expanded to be used in other techniques. Kinetics and thermodynamics, which I assume is the half that Ube teaches.
Yeah.
That is very useful for telling you how reactions are going to work. Are they going to go to side A or side B? How fast they're going to go? So PChem is very useful. In general term. Yulin's question. If I can find the correct slide.
Oh. They probably will.
It's kind of sick.
For so long.
You fucking stop. I will ruin your day today.
Do it.
I live with you.
So Yulin's question is on these two equations here. And he's wondering why the sum has to be equal to 1. So more specifically, the normalization of this has to be equal to 1, which involves an integral. This is a method that many textbooks use to get around that, doing that integral. So if you sum the square of the coefficients and have it equal to 1, it's normalized generally. And the reason we want it equal to 1 is we want to make sure that there is a probability that the electron will be within our states and not more than 1 electron or whatever particle we're interested in our states. So by setting this to 1, we're ensuring that our electron is in either state 1 or state 2. And I don't know why I said that opposite the way I pointed at them.
Midweek. It's just kind of how it is.
That makes sense, Yulin?
Getting in the end.
There any other questions?
So,
Sam, what's your question?
Sam always asks questions.
These goodies.
When does the fun begin?
Yeah, you're on lock.
Saying.
Pandora's box.
Fun has already begun.
Yeah,
Yes, that's the correct answer.
Yeah.
Good job, Melody.
That's really fun.
Well, if there are no other questions, we can be done with the class for today. It was good talking to you.
Yeah, this was great.
Yulin's the one, at least to my knowledge, Yulin's the one covering the lab. Right? And
Yulin, can you confirm?
don't honestly know what.
Confirm or
you're doing.
deny. If the answer is you cannot make it, that is okay.
Yeah, that's
If
fine.
the answer is he cannot make it, then I'm covering
Oh, okay.
Well, if you also can't come this.
it. Okay, thanks for being here.
Yeah, you too.
Yeah, thank you.
Appreciate you showing up.
Thank you for teaching us.
Otherwise, we'd have to go around just talking about what we know about PChem, you know?
Stop immediately.
I mean,
Melody would say something.
That's
Sam
at
would-
5, right?
Yeah,
Yeah.
5 to when it's.
1:38 or something. right?
Let's shoot for like 1 hour today.
Yeah,
David, there's like 5 chats from Hewlin.
Yeah, I'm
Okay.
Tom.
Oh, okay, oh. No, did Dimitri give it to us?